Okay, I'm on problem 4.50 here, page 185. And let me know where you're at on this in terms of time, because I'm working them through and it's taking me a while. And, I don't know if it's going to take you 2 hours or 2 days, or what the situation is, or how comfortable you are with this 3D stuff. But we were supposed to draw the energy diagram. I think having these guys here on this lesson, these lessons are probably very helpful. Draw the relative energy diagram showing the conformational analysis of 1,2-dichloroethane. Clearly label all staggered and eclipsed conformations with the corresponding Newman projections. I guess I didn't do that. So we want Newman projections like this. Let's see. I can maybe do that on the fly though. So it's ethane is the parent. Dichloroethane, one on the 1 and one on the 2. So what you've got here, that's an eclipsed chlorine to chlorine. So on this one here, you're going to have chlorine in the back, H, and in front, you're going to have C, L, H, that's eclipsed. And then you go a little bit to one side, let's say this one. That'll be staggered, so you'd have in the back still chlorine and hydrogen, and then on the front one you'd have chlorine, hydrogen, and then you can see that this would be eclipsed again, and then the next staggered you drop off the table, it's really down low here, so that one would be chlorine, H, but on the top you'd have, well, that'd be this one. I guess I could do that one. That's this one. So that one belongs here and here. And then as you go around, you're going back to a staggered or an eclipsed, chlorine on hydrogen, and then a staggered, and then an eclipsed. Now, it's more complicated than that on this one though, because chlorine is quite electronegative. So if it's over here like this, is that going to be a higher energy, or a little bit higher energy, or a lower energy? It's probably pretty close to this, but it is more complicated when you got something that's electronegative with something that isn't very electronegative. Okay, 451. All right. They want us to see what we got here. It says assign the names. Well, that one I have. You're looking at the 2 carbons in down the Newman projection. This is the back one. This is the front one. So you had a methane off the bottom of the back one, and off the front you have 1, 2, 3. So this is what you're drawing. It's just hexane is all that is. And then on B, you've got a ring. And in that ring, if you're looking down, it doesn't matter where you put that methane, it turns out, because there's only one. But you're looking down, let's say these 2 carbons and these 2 carbons, and this is in the front and that's in the back. You got a methane off the back. So it's just a methylhexane, and you can put that methyl wherever you want, really, in your drawing. C, there's a carbon in the front, carbon in the back, and the 3 other ones. So that's a pentane with a methyl off of it, so it's just a methylpentane. D is a dimethylpentane. You have a methyl off the front, methyl off the back. Oh, sorry. I screwed these up, didn't I? This one is methylcyclohexane. And this one is methylcyclopentane. And this one is dimethylcyclopentane. Cyclopentane. Okay? Forgot the cyclos. All right, I think I'm done with this guy. I don't really know what they want on this one exactly, so I'll tell you what I think the answer's supposed to be. It depends on how you look at it, and I could argue it a couple different ways. But here's what I think they want. You've got a bromoethane. And they're talking about rotating it. And they're saying the barrier to rotation is 15 kilojoules per mole. Now, the way I read that, that's going to take 15 kilojoules per mole to make a rotation around. Like so. Now, the problem is, it's kind of like stored energy of a spring. If you input some there, you should get some out here. Input some there, get some out here. Input some there, you should get some out there. So really, to go all the way around, in a sense, it wouldn't take any net if you added them all up together. But I don't think that's what they're doing. So if you're going to eclipse it, what's the energy with each one? So if I take the 15 and say I've got to eclipse it here and here and here, I'm thinking that that's 5 apiece is the way they're counting that. Although I don't really count it that way because you're pushing off the next one. But I think that's what they want. 5 kilojoules per mole to eclipse it. And if that energy was an attractive one, because this is a little bit electronegative, then it would be negative. I think it's positive though. So I think that's what they want on that one, but it's hard for me to read the tea leaves and see what they want on that one. It's a little bit of a bizarre question. It's an interesting one. I think it's worth talking about. I just think that the answer, depending on how you look at it, is arguable. Whatever they consider that answer to be. Okay, on to 453 menthol. Is isolated from mint oils. It's used in the treatment, just like in cough drops and stuff. Draw both Kacher conformations and indicate which one is lower in energy. So it looks to me, I imagine, I don't know how else since I did this. I think I called that the 1 carbon and the 3 carbon and the 4 carbon. That's what it looks like. So that methyl group is up. And then 2 positions over, I have a hydroxyl group that's up, not down. And then I have a isopropyl group is down. And then if I flip the chair around, this comes up to axial. 2 positions over, this is going to go up to axial. This is going to go down to axial. So this is obviously not, there's a lot of interference here. I didn't look it up on the table to see what it is, but we could do that. Remind you that that's where that table comes in here. That's what I was doing, I think, on the last video. Where was that? See, we have an isopropyl, I think. Yeah, that's 9.2. Hydroxide 4.2. Okay, yeah, we've got it. This is 9.2, this is 4.2, and I think this is 7.6 for this guy. All that together, whatever that adds up to, I mean, that's like in the realm of 20 or so, more than 20. Okay, 20 plus. So this is by far preferred. Those are all equatorial. There's no interactions there to speak of. Draw the chair conformations for each of the following compounds and identify the more stable chair conformation. And again, be on the lookout for what you think a mistake is, because they can be all over the place. I found a few. I found some while I was going through this. All right, on A, I have methyl cyclohexane. So it's just a cyclohexane with a methyl on it. I can put it in either position. If I put it here and flip it this way, this is going to have an interaction that's going to be a 7.2, so this is going to be the more stable. B, trans 1,2-diisopropyl cyclohexane. Okay, so I've got my cyclohexane here. Off my 1 position, I've got an isopropyl. Off my 2 position, I've got an isopropyl. It's trans because this one is up as opposed to the down hydrogen. This one is down as opposed to the axial hydrogen. I meant to say axial down here. Okay, so if I flip this one up, it becomes axial. Flip this one down, it becomes axial. This is more stable because the interference on here is, what did I say it was last time? 9.2 for an isopropyl. Yeah, it's a 9.2. So this combined is an 18.4 steric interference on the inner side. So this is way more stable. All right. C, what I came up with was where am I at? 4.54. Something's wrong. No, okay, it's okay. Cis 1,3-diisopropyl cyclohexane. Now, because I'm another carbon position out, if this is the 1 and this is a 3, I should get kind of the same result all over again. This is up. Then C is cis. This is up. The axials are down. That's hydrogen on those. If I flip the chair the other way, the interference here should be about 18.4 or so, because it's 9.2 doubled. So this is way more stable. And if I go to the 4th position out here, this one's up, this one is down, so this is trans, because the hydrogen is axial here and there. So if I flip the chair, this one is up, and this one is down. Again, this is about 18.4, or whatever I said it was earlier. So the more stable one is the one on the left. 45. This is a lot of drawing. Did find a mistake or two here, so this is easy to do. We're comparing this guy to this guy. When I get to the bottom one, I got to remember I numbered it differently. So I probably called that number 1, 3, and 5. 1, 3, and 5. Let's take a look. Yeah, so I've got an up here. That's the 1 position. 3 is up as opposed to axial. Ooh, I did this wrong. It should be this way, not down that way. Okay, and then the axial is here. And then the one on the left, that's down. So then if I flip the chair the other way, this is up, and this is equatorial. And so I only have one that's directly interfering here. If we draw the compound on the right, so we want to draw the 2 chair conformations for this one on the bottom, and then compare to see what's better. Okay, those are all down. So in the 1 position I have a down, 3 position down, 5 position down. This is a big no-no here, because that's all interfering. That'd be 7.2 times 3 is 621.6 interference. The other chairs, equatorial, got pretty much nothing there. So this should be, since there's very little interference, this should be the preferred. Because it's the most stable. The other one has a 7.2 interference right there, and this is 14 or 15 point, I guess these were 7.6s, weren't they? So this is 15.2, and this would be, what, 22.8. But this is still preferred. So the one that is more stable is this one, as long as, and it will, when it's made, it jumps to this chair conformation. Okay, I'll get done with this one. This one may run a little over too, but this will be done. And then I probably call this the number 1, 2, and 3 position, 1, 2, and 3. In the first one, I have 1 is down, equatory 2 is up, 3 is down. Sterically, this is going to be 7.6 times 3, so it's 22.8. This is a big boo-hoo. This is about 0, so this should be preferred. Okay. And on this one, I've got a 7.6 for that and a 15.2 for these two. So if you make this compound, it's going to jump to that conformation, and this is what you're going to have. So we'll prefer the one on the left. And continue with the last two here. We'll put the other ones on another video. So I've got the 1 and 3 position both up here. And on the one on the left, this is the other chair conformation. This is not going to happen. This is going to be preferred because there's no interference here. The one on the right, I've got it down. I'm calling this the 1 carbon, 2, 3 carbon, 1 carbon, 3 carbon. I'm calling this my 1 carbon. I've got it down and an up that's equatorial. When I flip the chair, this is up and that's still down. So this is a 7.6 here. This is a 7.6 interference here. So the one that's going to happen is you're going to make this compound and it's going to prefer that orientation, that chair conformation. And one more. This is D. The difference is on this one is I call this my 1 carbon, 2, 3, 4, and 5. So usually you kind of go to the most clockwise, counterclockwise one. I call this one 1 and this one 3, 1, 2, and 4 and 5. So I have an up and a down. This one's equatorial. Skip, and then no, wait a minute, an up, yeah, and a down, and then a down because that's what's axial there, and then an up, which is equatorial. And then if I flip it, this is not going to happen because it's 7.6 times 4, whatever that is, 34 points. I don't know, it's high. This is about 0. The other compound, I've got an up and a down equatorial, and then an up axial and then a down axial. And if I flip it, then I've got axial, axial, equatorial, equatorial. In both of these cases, I've got 2 that are axial, so it's 15.2 and 15.2 over here for these two. So the preferred one is going to be the one on the left, and it's going to be this one, and it's going to be this chair conformation.